So let's look at how exponential growth functions and exponential decay functions are used in real life. We've already gone over a couple of these examples in class, but let's look at a couple more here in this video. Recall that our exponential function has the form y equals a multiplied by b to the x. When we have something in real life that we want to apply this model towards, we change up only a couple of parts of the function. It's y equals a multiplied by, now our b becomes this 1 plus r, and our x just gets changed to t. Our a is still what stretches or shrinks the graph, but what it represents in terms of actual real life scenarios is the initial amount. So since we're going to deal with growth functions, exponential growth functions, we know that we're going to have something that's going to grow, whether it's number of people, number, in our example that we're going to do here is viruses. In class we did number of buffalo. Whatever it is that you're starting with, this is your initial amount. It's your A. 1 plus R, it's called the growth factor. It's how much it's actually growing by. R is your rate. It's represented, it should be represented in terms of decimals. So if you have a percentage, you're going to have to convert that to decimals before you punch it into your calculator, apply it into this formula. And T represents time, how much time has passed, and it is represented in years. So let's see how this would work in real life. Let's look at one of the examples from the book. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. Write an exponential growth model giving the number n of incidents t years after 1996. How many incidents were there in 2003? So let's go back at our model. Let's look at that. Now what they want, we're going to change this y. We're going to change it to an n. I'm sorry, I didn't specify this, but the y in our function, this y here, represents the end amount. So a, remember, is our initial amount, but after we apply the growth factor and the time to a, we're going to end up with the end amount. How many buffalo, how many viruses, how many people are there after X many years have passed, or T many years have passed. In this case, they want n number of incidents. So how many incidents were there after 1996? So what is our initial amount? Well, they said that in 1996, which is where we started, there were 2,573 computer viruses. Now let's apply into our 1 plus R. What's the R that they give us? It's percentage. They're saying it increased by 92% each year. So how do we represent 92%? 0.92. So remember, you have to know how to do conversions from percentages to decimals. And they're saying that they're giving it to us, well, the question that they're asking is how many incidents were there in 2003? How many years, you have to ask yourself, how many years have passed from 1996 to 2003? Well, there was 1997 was the first year, 8 was the second year, 1999, 2000, 2001, 2002, 2003. There were 7 years that passed from 1996 to 2003. So there it is. That is the answer for, that is the growth model. That's not the answer. That's the growth model for 7 years after 1993. We can rewrite this as saying n equals 2,573 multiplied by 1.92 to the 7th power. So now let's open up a calculator. Oh yeah, my computer does not have internet. So there's no way for me to be able to calculate this for you guys here. What you should do is either go on Google, look up a calculator, punch it into your own calculator if you have one. You would punch in 1.92 to the 7th power. You always want to take care of the exponents first. Remember, that's just basic laws of PEMDAS, if you remember PEMDAS. Always take care of the exponents first. So take care of this part first. Once you raise 1.92 to the 7th, then multiply it to 2,573, and you're going to get the end amount of viruses in 2003. Graph the model. We're not going to worry about graphing the model, so let's go on to the next problem. Okay, let's look at decay now. That first problem that we worked on was growth. How do we know that it was growth? How do we know that this one is going to be decay? Well, let's look at keywords here. It says for the growth model, the virus is increased. So when something's increasing, it's getting larger, it's growing. So we use exponential growth. This time it's going to be decaying. So let's read the prompt, let's read the question and see how we know if we didn't have this marker here telling us that it was decay. How will we know that it was decay? So let's read the prompt. The pesticide DDT was widely used in the United States until its ban in 1972. DDT is toxic to a wide range of animals and aquatic life, and is suspected to cause cancer in humans. The half-life of DDT can be 15 or more years. Half-life is the amount of time it takes for half of the amount of a substance to decay. There it is. Boom. Decay. So if this is said that it was going down by half, if it said decay, it said it's decreasing, we know we're going to use the decay model, not the growth model. Let's keep going. Scientists and environmentalists worry about such substances because these hazardous materials continue to be dangerous for many years after their disposal. For this example, we will set the half-life of the pesticide DDT to be 15 years. So let's first examine the question, see exactly what it's asking, what it's talking. Okay, so let's examine the question. So pesticide DDT, what it is, pesticide, if you're not familiar with that term, it's a chemical substance that's sprayed to kill things. So to kill animals, to kill bugs, to kill bacteria. So this was sprayed all around the United States until it was banned in 1972, and it was banned because it's toxic to animals, aquatic life, which fish, and it's expected to cause cancer in humans. So it makes humans very sick with cancer. So it was banned. Now half-life, it explained it to you here, but let me explain it to you. What a half-life is it's the amount of time it takes a substance, a chemical substance, to decay, to erode, to be reduced to half of the original size. So if you're starting off with 10 grams of something, once one half-life cycle passes, instead of being left with 10, you're left with half of that, which is 5. Then another half-life cycle passes. Instead of being left with 5 grams, you're now left with 2.5. And it keeps on continuing like that. So here we know that we are having decay. We also know that it's half-life. So the amount that it's decaying by is half. So it's 50% of the original amount is being eroded. So what we're going to change here in our function is instead of saying y is equal to a multiplied by 1 plus r, remember now we have decay, so this becomes 1 minus r. Anytime you have decay, since things are going down, things are breaking down, you're going to have a subtraction, and then t. So it looks like I cut off the question, but the question prompt said if you start off with 100 grams of pesticide, first write out a decay function model, and then say how many grams there are after 1 year, after 2 years, after 3 years, and so on. So first, let's plug in the information that we have into our model. So y is equal to our initial amount, a. Our initial amount, we were told that it's 100. Plug in 100 there. multiplied by 1 minus r. Now remember, this is decaying by half, so it's going down by 50%, which is half. So 50% in decimals is 0.5. And now we're going to raise it to the t exponent. T would represent how many cycles, how many times the half-life cycle has passed. So this becomes 100 multiplied by what's 1 minus 0.5, 0.5, to the t. So let's take this and work with it a little bit. Come here, please. U2. Come down. There we go. So, we started off with 100 grams of DDT. How many grams were left after one cycle? Notice the change. Now I'm not saying after 1 year. I'm saying after one cycle. Every cycle takes 15 years. But that's not what we plug in here. We're not going to plug in 15 every single time. This T doesn't always represent years, singular years. It can also represent cycles. And every cycle represents, in this case, 15 years. So we're going to have one cycle. So this is 100 multiplied by 0.5, 0.5 to the first exponent, which is 100 multiplied by 1/2, and what's 1/2 of 100? It's 50. Now our next cycle would pass. We would plug in a 2 into this T, and this 50 would go down to 25, because remember, we go to half-life, and half just means it keeps going down by half. Let's keep going. What's half of 25? A third cycle would pass. We'd have 12.5. And then another cycle would happen, and we have 6.25. And then another cycle, and it keeps going, and it keeps going, and it keeps going, and it keeps going. But the thing that you need to know about half-life, or about decay, is that decay is never going to get to 0. These things are going to go down and down and down. They're going to get lower and smaller and smaller and smaller and smaller. But there's always going to be something there. Let me see if I can show you here. Here it goes. After one cycle of this DDT half-life, left with 50, 25, 12.5, 6.25. It keeps getting smaller, and it's getting smaller, and it's getting very, very small. After 10 cycles, or after 150 years, you still have very small amounts of DDT, but it's there. The next cycle would pass, and you would have an even smaller amount of DDT, but it's still there. So anytime you have decay, what you need to be aware of is that you're always going to have an amount there. So try it out on your calculator. Get any amount that you want, punch any amount that you want on the calculator, whether it be 10 or 50 or 100 or 10,000, and try a half-life experiment, if you will. Multiply with the amount that you put in by 0.5, which is you're multiplying it by half. Multiply that by 0.5, and that by 0.5, and that by 0.5, and keep going. Keep running through cycles of half-life. Do you ever get 0? You shouldn't. The number should get smaller and smaller and smaller, but the number should always be there.